My name is Joon. I will talk about injection moldable, reflow compatible thermoplastic solutions for optical interconnectors mainly in data centers. First, the SABIC introduction. SABIC is a material supplier. We supply chemicals, thermoplastics, specialty thermoplastics, and agri-nutrient. SABIC is second largest in chemical industry globally, and we have around 29,000 employees around the world. Looks like the biggest company in this group. Also, we have around 38 billion annual revenue this year. So I'm from specialties business unit, and I will briefly talk about what specialties thermoplastic means. I believe most of you are familiar with PC or polycarbonate, PMMA. So those here we have the material pyramid from lower temperature resistance to higher temperatures. So standard PC, PMMA, they are resistant up to around 180 degrees. So these are called engineering thermoplastics. To higher temperature resistance materials, those are usually considered as a specialty grade, for example, PC copolymers. Then we also have higher end specialty materials such as polyether. The brand name is EXTEM. So EXTEM is near IR transparent. Of course, it's injection moldable and it's extremely stable in dimensions, even at high temperature around 240 degrees. So you can also use low temperature soldering process. Then we have the unique material called EXTEM. There's a thermoplastic polyimide, as it means thermoplastic, it's injection moldable or metal processable. That is contrary to this PAI, or known as a kind of kaptons. So that you can either extrude or mold, but it's not a completely solid state. You need additional curing that can take several hours to, in cases a few days. So this EXTEM is completely injection moldable. Once you mold, that's your final product. The uniqueness of this material is it contains all the benefits of this EXTEM resins. So it's injection moldable, and it has extreme high temperature resistance up to 280 degrees. So you can use this material for reflow soldering. So in the electronics industry, all the electronic components are placed on the PCB. It goes through reflow oven. And in the reflow oven, temperature can go up to 260 degrees. That is industry standard. Quite often people think, okay, thermoplastic, at that high temperature, it will melt down. But that's not really the case. So we have IR transparent, injection moldable, reflow capable materials. So here we have some material properties, like light transmission at different wavelengths, refractive index. But of course, you don't need to remember. If you need more data, we can provide optical constant. Also, these optical constants are already included either in ANSYS JMAX or COMSOL, so you can simply upload the material library. On the right-hand side, we plot the light transmission with respect to the wavelengths. So spectral transmission, here we emphasize the two typical wavelengths. At 850, this is quite often used in multimode fiber optics, also near IR sensors. Also here, another point, at 1310, this is quite often used for single mode fiber optics. Here, as you can see, we have over around 87–88% transmission at 1 millimeter without any AR coating. If you want even higher light transmission, you can apply AR coating. It causes some additional cost, of course. Then you can go well above 95% of light transmission. Also critical, more importantly, it can go through the 3 times 260 JEDEC standard reflow process. Also here, we did 85,000 hour Telcordia hydro testing. You don't see any drop of the light transmission. Also on the right-hand side, here we shows one prototyping samples. So it has 3x4 micro lens arrays, rough size around 5 millimeter by 5 millimeter. Also, it went through 3 times reflow, 1,000 hours hydro testing. You don't see any crack or something here. So then, okay, we have the materials. Then what does it mean in actual applications? So in the current data centers, So we have some kind of IC chips, either CPU or GPUs. Then in the telecom industry, the data is communicated optically quite often. Then there should be some kind of the signal converter between optical signal to electronic and vice versa. So they are currently, you see the racks of these supercomputers. Then these are, how say, plugged and unplugged at the end of the rack. So that is the current infrastructure at the data centers. There, our EXTEM resin is already used for this ROSA and TOSA element, so receiving and transmitting element. Also, since it's injection moldable, it's not only lens element, but in this case, for example, there's a kind of the housing that can encapsulate some electronic component, like either VEX laser module or photodiode. So you can just simply mold one single piece for multiple purposes. Yeah. Here we showed this TOSA ROSA, but these EXTEM elements are also widely used in other applications, such kind of the active optical cables or expanded beam connectors, etc. In the new trend of the data centers, actually the optical chip, optical module is integrated with the electronic component that brings that can remove this copper wire, and it can increase the data transfer rate up to a factor of 5. Also, it will reduce the power consumption. We all know that these AI booms, there are multiple issues of electricity consumption. So that is the trend we learned from the industry. Then our EXTEM resin can be used as optical module here, and it can go through the reflow process. So here, it's the part we designed with our customer molder, Nelux, in Japan. So for example, here we use the 2 pins like this. It can directly connect it to MPO type of connectors. Then also you can see there are 4 lenses, additional 4 lenses on the front face. So it can be connected to the fiber modules. Then on these lenses front will expand the light from the fiber, and there's kind of a prism or total internal reflection mirror. So also it can bend the light towards the IC chip on the PCB side. Also here, you don't need any metallization or secondary operation because a high refractive index, light will bend by physics. Also there's another lens, additional set of lens arrays on the bottom that will either focus or collimate from the peak side. Yeah. Then, by the way, here, this is multi-mode optics. Then also our material can be used single-mode optics. Single-mode optics has advantage to transfer high transfer data to longer distance. But there, the fiber core is much smaller, so we need a lot tighter tolerance. In this case, so we developed single-mode co-packaged optics with the Tyndall Institute, also Dell as well. So in this case, the design is relatively simple. We have one-dimensional micro lens arrays, each is spaced at 250 micrometer distance. Then, these are 2 identical lenses. One is glued to this fiber array. So signal comes through this fiber array and passing through this lens, and it is expanded. Then it goes to another micro lens array, bonded on this peak. Then the light is greater coupled to this peak, and we have the waveguide loop. So it passes through the next lens, and it goes open space. It goes to another lens, and again fiber arrays. Then we can also measure the signal through this unit, so it allows the communication over free space. Also, you have the possibility to plug and unplug. Yeah. So here you can clearly see the eye diagram and enough margin to the mask of IEEE standard. Yeah. Then also we claimed that it's reflow compatible. So this black line is actually the the signal loss or coupling efficiency with respect to the wavelength. Here you can already see it's a bit, high signal loss observed, but that is not because of our lens. Actually, the peak is not, optimized for this demonstrator. We just utilized existing peak and also existing packaging technology. So Tyndall confirmed that it is based on the peak design and more like assembling technology, not by our lens. Also, after reflow, you can see they are almost overlapping each other. Then also, here also we measured the lens geometry by using metrology. Also, after 3 times reflow, even MSL1 condition, you don't see much dimensional change. By the way, MSL condition is the moisture sensitivity level before the reflow process in the semiconductor industry. All the electronic packagings are, they shipped in a sealed package, and once you open the package, how long the part can withstand or to reabsorb moisture before going to the reflow process. So also our material can withstand MSL1. But this MSL condition is not only material dependent, it can also dependent on the part design. For example, if you have a thicker part, then the moisture can take more time to escape during the earlier, the temperature pick up in the reflow cycle. So in that case, it may pass MSL3 conditions, for example. Yeah. Then, up until now, we talked all about the good things of our materials, but we are honest, there's also some shortcomings. Yeah. So here we showed the coefficient of thermal expansion, or CTE. Then our materials here, EXTEM and EXTEM, actually they have lower CTE than other competitive grade. Also, we have this low CT EXTEM resin, which has around 35 to 40 ppm per degrees. So it's extremely low as a thermoplastics, but in the photonic integrating package, actually these lenses should be aligned with a peak that is kind of or glass. Then there's a huge difference of the CTE. So there, of course, glass lenses has intrinsic advantage in short period of time. Most probably, thermoplastic cannot match the CTE of glass. But that's not the end of the story. So even though our material has higher CTE, you can mitigate some other aspects, like the CT mitigation is a long history in mechanical engineering. For example, in this case, we also did the simulation using this MPO type of connectors. So in the MPO type connectors, there's 2 metal pins, for example. So also we added this kind of design features. In this case, we have 12 micro lens arrays. Then also we did a stub analysis, structural, thermal, and optical performance analysis. In this case, so we assumed these 2 pins completely blocking the movement of these micro lens arrays. In these 2 cases, we only restricted the expansion only one side, then they can freely expand and shrink. Then you can see a lot higher also lateral misalignment and signal loss. But by constraining that kind of the expansion, it will bulge in a 3-dimensional direction. But laterally, these lenses are still aligned to either fiber side or peak side, and you can still see very minimal signal loss. Yeah. So in this talk, we mainly talked about this thermoplastic resin solution, which is reflow compatible for mainly this kind of the optical interconnect in data centers, but it can be used for other applications as well, such kind of a time of flight sensor. Here you see 2 lenses, one is receiving, the other one is transmitting side. Also, our customer molded this kind of a highly aspherical micro lens array that can diffuse the light in a wide angle. So it is used as a wide angle time of flight sensor. Also, you can imagine multiple other applications. So these materials can allow complex design shapes, such as freeform optics or fixtures or whatever you can imagine. Then it will allow cost-efficient production. But that is not only cost-efficient production in the lens manufacturing. Since this is reflow compatible, it will also allow mass producibility in a packaging or assembling side. And last but not the least, our material is not export-controlled, non-hazardous to mold or convert. So wherever you need the material, either in Europe, Asia Pacific, or US, we can supply that. Yeah. Okay. Thank you.